G'day chemists. So today we're going to look at enthalpy, in particular exothermic and endothermic reactions. This is like an intro to enthalpy. So our learning goal here is to be able to explain the difference between an exothermic and an endothermic reaction using that language, the language of enthalpy. This here is your vocabulary. If I could just get you to quickly pause this video, and then we'll have something to refer back to as we continue on. I will point you to exothermic and endothermic though in particular. However, enthalpy and enthalpy change, that's the language we want to learn to use as we're moving through. So what is enthalpy? Basically, it's the heat or the heat energy stored in chemical bonds. Now, the unit for that is joules, although we'll often use kilojoules. Joules is a name, so it's a proper noun, but in this case we're using it as a noun, so it's a lowercase j. As the symbol, it's always a capital J. Enthalpy change, so that's what this delta, this sort of triangle here means, right? Enthalpy change is the comparison of energy between the products and the reactants. And I actually want you to draw your attention over here to start off with. Here, if we end up with our initial reactants and our final products, the really cool thing about enthalpy is that it's a state-dependent change. In other words, the path you use to get there is irrelevant. You could use a direct reaction, or a reaction that has an extra step in there, or a reaction that has two extra steps. It doesn't matter. The enthalpy change only depends on the state of all the reactants and the state of all the products. Everything in between is irrelevant. So again, the unit for enthalpy change is joules per mole. So when we're talking about how many moles of a certain reaction have gone through, then it's joules per mole. So enthalpy change is that summary, right, of the intermediary. And that's what we mean by it's a state reaction. So the enthalpy change is a summary of all of the changes. So this one minus this. And all of these changes here added together give us our final enthalpy change. One of the ways to calculate this is the change in the heat of reaction, or enthalpy of reaction, is the sum of the enthalpy of the products. Now notice, by the way, where the R accent, that's for reaction, is. It's on the left side of the H, in between the delta and the H. And here there is no delta, so it's on the right side of the H. Anyway, it doesn't really matter if you get that backwards. Everyone will know what you mean, and that's completely fine. So delta H equals the sum of the enthalpy of the products, so that's here, so all the sum of the enthalpies of the energy stored in the bonds, minus the sum of the energies stored in the bonds of the initial reactants. And that gives us that change. So photosynthesis and respiration, let's have a look at this. So here's our photosynthesis. In fact, this is respiration. Photosynthesis goes this way. We're using kilocalories here instead of kilojoules. It doesn't matter. We can see the same. We'll see how to see what we're talking about. So here, if we go this way, we see that delta H increases. Okay. In photosynthesis, there is more energy stored in the products than there are in the reactants. Whereas if we go the other direction, for respiration, we see that so that's the using of the energy, we see that there's more energy stored in the reactants than there are the products. And this means that respiration is an exothermic reaction. It releases energy. It releases energy because it's got more energy stored in the in the reactants than there are the products. So I hope that makes sense. That might be a good point to pause, write down some questions if you have any, and if you want, just pop them in the comments and we'll get back to you. So let's talk specifically about exothermic and endothermic reactions. We'll start with exothermic because it's the one that goes boom, so I enjoy it. Exothermic reactions release energy. So this means that we can actually write energy as a product of the reaction. So reactants have more potential energy or more heat energy stored in their bonds than the products. And that's what we see here, right? This hump is the activation energy. Don't worry about that for the moment. But here's the energy stored in the reactants, and here's the energy stored in the bonds of the products. And we see that there's more here. And this gap between the two is our delta H. That's our change in enthalpy. So, and this means energy is a product of the reaction. Okay. Now, as it is delta H product minus sigma of the, those delta H equals the sigma, so sum of, energy stored in the products, bonds, minus the energy stored in the reactants. Because there's more energy stored in the reactants, that means for an exothermic reaction, delta H is always a negative number. And so they'll always have a negative delta H, and they'll always release energy. One of the ways we can check this is that the temperature of the environment increases. Delta H we can't actually measure directly, so we use measures of environmental change to see what the difference is between the energy stored in the bonds. So now let's have a look at an endothermic reaction. Endothermic reactions absorb energy, okay, and we can see that in our graph here. We have more energy stored in the products than we do the reactants. That's the activation energy, so ignore that part for the moment. And we see that the reaction has to climb up here, so the bonds have more energy, so it has to absorb energy. Energy is a reactant in the reaction. So products have more potential energy stored in the bonds than the reactants. Nice, pretty straightforward. Therefore, energy is a reactant. So that's just explaining using the language of enthalpy why this is the case. So the delta H of the reaction is the delta H of the products minus the delta H of the reactants. The products is higher, okay? There's more energy stored in the reactants. Therefore, we end up with a positive change. Because if we have a higher number, say 10, and we take away a smaller number, 5, we're going to have something left over. And in this case, endothermic reactions will always have a positive delta H. And we can check this by noticing that the temperature of the environment decreases. That's incorrect. That should say decreases. And we'll fix that later. I hope that made sense. If you have any questions, put them in the comments below. We'll get back to you as quick as we can. Thanks for watching, and we'll catch you next time. Bye now.